Oh, no, that's okay. So guys, today what we're going to do is we are going to wrap up chapter 17 and wrap up this unit by looking at weak titrations. So again, guys, and I know that you're aware of this, but the idea is the thing that is weak is the thing that we are titrating, and then the thing that we are using as the titrant is strong. Right? So we've got a strong acid or a strong base going into a weak base or a weak acid. Now guys, what you're going to find is that this will feel, if you can consider this an emotion, this will feel a lot like titrating buffers, right? The stuff that we did with iRace boxes when we were adding strong titrants to buffers, it's kind of like that, but it's different enough that instead of anchoring it to that, guys, what we're going to do is this. So we're going to have a moment of silence so Everett can sharpen. And now, guys, what we're going to do is we are going to anchor this entire conversation to this. So don't go low, stay high. Guys, the top of this is a graphical summary of everything that we talked about in 2 days ago's class, where we talked about how to solve strong titration problems. And guys, notice across the top, what do these 4 categories represent? Yeah, the 4 regions. I like that you're doing this. The 4 regions on the titration curve. So we have the initial pH, and guys, let's just say we're dumping a base into an acid. So we've got the initial pH of the acid. We've got the pH before equivalence. And guys, notice how I described the math. I said the pH before equivalence is equal to the concentration of the unreacted ion, that could be the acid, and is found by subtracting, right? We figure out the moles of one, we figure out the moles of other, we subtract. The difference is the number of moles of unreacted ion. Then we convert that to a molarity, remembering that the volume is changing because we're adding liquids together, solutions together. So we divide by the adjusted volume. That becomes the molarity that we then take the negative log of to find pH. Is that all ringing true with you? Okay, then, what? And yeah, so here, okay, so we can relate this to the graph, right? So the idea is if we go here, and then if we go here, so the idea then for a okay, that works, and that, and that. Okay, because when it's done this in the past, very soon my whole computer is going to freeze. We'll see how it goes. So yeah, Nate, so the idea is this. Okay, this is not going to, so I can write here, it just has no, you'd think for $4,000 this thing would work. So, okay, I'm going to rant for just a second. So, Epson, like Epson Corporate, called me. They're very concerned about this because they realize that I'm a demo guy for this. And if I go, hey, this is neat, then Alpine School District buys hundreds of these. If I go, hey, this is not so neat, then they don't sell any of these to us. So they're concerned that I like their product. And I've told them that this thing doesn't track very well. Their first question was, how tall are you? Because they think my head is in the way. So then when I said I'm 5 inches tall, they go, okay, that's not it. So then they say, when you teach, how animated are you? Because if you're flapping your arms around, that could be the problem. They blamed it on me. They're telling me that the issue is with me and not their technology. So, needless to say, They're flying somebody out at the end of the month. Okay, so Nate, to your question, maybe. Yeah, sorry, hold on, let me put this in my pocket. Maybe that's the problem. Okay, so what we're saying, Nate, is this. So the initial concentration in the initial molar or pH in a strong titration is just the negative log of the concentration of the acid because it completely dissociates. In this region right here, before equivalence, what we've got is we've got the initial amount of acid, we'll say, and then we're adding base to it. And the base is consuming the acid, and the pH is found by the amount of acid that hasn't been consumed. So how do we know how much acid hasn't been consumed? And that's what this is speaking of. The idea is that we're subtracting. So how much acid did we start with? And again, Gavin, in moles. And then how much base did we add in moles? And why are these done in moles? Because they're strong and this is quantitative. Subtract those two. That gives you the amount that hasn't been neutralized. And then by converting that to a molarity by dividing by volume, that gives you concentration. Negative log gives you pH. Is that okay? So now, guys, what about this big old dude? In a strong titration, what do we know about the pH at equivalence? It's 7. Why is that true? Because the salt that is formed, because it's a strong titration, the salt that is formed, by definition, is the child of a strong acid and a strong base, and those ions do not mess around with water. They're worthless conjugates, and so the pH is right at 7. You good on that? Now, guys, notice what I wrote for after equivalence. Compare it to before equivalence. What do you notice? They're the same, right? But guys, how does that work? Well, the idea is that after equivalence, now instead of having unreacted acid, we have unreacted base. So all of the base that we've added up to equivalence has been neutralized by the acid. If we go past equivalence, then what we're doing is we are adding additional base, which is then unreacted, and we can find out how much additional base we have, again through a subtraction, which we then convert to a molarity by dividing by the new volume, and then take the negative log to find, in this case, POH, which we can then convert to pH. So, questions, good summary, right? Good review. Anything here you need to talk about? You guys are okay? Okay, yeah. Are you sure? Okay, if it seems pertinent, come back to it. So guys, now what we're going to do is this. We are going to have that same conversation around weak titrations. I've given you all the notes down here. This is everything that you need to know. So here's the way today is going to go. We are going to take a titration curve for a strong acid base. That's this. And we are going to superimpose onto the top of it the titration for a weak acid or base. So for those of you that are in lab, it's as if the last lab that we did where you printed your graphs, it's as if you took your two graphs, one from titrating hydrochloric acid, one from titrating acetic acid, and laid them on top of each other. That's what we're going to do. And we are going to talk about, first qualitatively, we're going to talk about the differences between the two titrations. Then, guys, we're going to have the same conversation mathematically. And this is going to be the summary of those conversations relative to the math. Then we're going to do some of this math. And guys, honestly, this math gets tricky. We're going to have to really slow down and think our way through it. And so we're going to solve two problems, and that's going to consume our day. You ready to go? Okay, so what do these look like? So here we have where we're at right now. Just sort of soak it in for a minute. This is the graph that we looked at before. Guys, how do we know that we're titrating an acid and not a base? Because it starts at a low pH, right? And so we understand that we're adding base to the acid. That, of course, is given to us. And just for reference sake, we've got 50 milliliters of 1 molar hydrochloric acid. We've got we've got titrant, which is 1 molar base, sodium hydroxide. We talked about endpoints and equivalence points. Guys, all of this should be familiar to you. You okay? And again, we talked about the pH initially, before equivalence, at equivalence, which is pH 7, and then beyond equivalence. All that familiar? It's comfortable? Okay. So now, guys, let's superimpose on top of that a weak titration curve, which is given to you in green. Now, guys, let me set the stage for this. So the blue represents the titration of 1 molar HCl, right? I hope I can write that down. So this is 1 molar HCl, so that's this. Guys, the other is 1 molar acetic acid. So this green curve represents the titration of 1 molar acetic acid. So guys, spend a couple seconds, compare the two, and then I'd like to talk about the similarities and differences. Given the blue curve that we're comfortable with, let's compare the green curve and talk about the similarities and differences. So what do you notice? What are the things that stand out to you as we now talk about the titration of a weak acid? Let's start with initially. Say it again. It's not as acidic. But guys, realize that could just be because they're not as concentrated. But because we know that these are equal molar, guys, why is the initial pH of the acetic acid above the pH of the HCl? Less of it dissociates. It's a weak acid. So guys, we would expect that pH, given that they're equal molarities, we would expect the pH to be higher because it's a weak acid. Again, understand that it could be because it's just less concentrated, but because the molarities are the same, that makes sense. Yes?
The pH rises at a different rate.
Yes.
Depending on how many milliliters.
Yeah, let's talk about that really quickly. And Carson, you and I have been sort of skirting this issue a little bit. But guys, did you notice what Spencer noticed? Guys, the initial titration of the strong acid is very, very linear. Its slope or its rate of change of pH is very linear. But you'll notice what's happening here. And we're not going to get deep into the chemistry, but we can talk about it. Initially, the increase in pH is very rapid, and then it becomes linear, a little more rapid in rate than the initial for the strong acid. But guys, what is going on with this initial change in pH, which is very rapid? And the answer is this: you are dumping a strong base into a weak acid. And initially, that weak acid is overwhelmed by the addition of that strong base. But then, very rapidly, it buffers itself. I can show you the chemistry. Well, I can. I don't know if my board can. Just one second. Guys, the chemistry looks like this. I'm going to switch colors. What we're doing is we are adding, so we've got the CH3COOH, and as we add NaOH to this, right, so we're adding base, what that forms is CH3COO, and then the water, which is the other product, as the base takes the hydrogens. But you start to look at this, and as we titrate this, this goes down and this goes up, right? And very quickly we create a buffer. Classic buffer, right? We've got a weak electrolyte in a common ion, and that creates a buffer. And as this buffers itself, the change in pH becomes less rapid, because as it buffers itself, the equilibrium compensates for what's going on. Yeah. Well, but there's, in this example, let me answer it two ways. In this example, you couldn't have an unbuffered acetic acid solution because it's buffering itself. So what about this? And you can't, but what if you could slurp out the acetate as it's being formed, right? Just take, sorry, this should be negative. What if you could take out the acetate as it's being formed, thereby creating that unbuffered solution? And the answer is yes, this would just increase like that. So if you could find a way to keep it from self-buffering, then that would indicate the change in pH, but you can't because it self-buffers. Did that kind of get to your question? Okay, so guys, we've got that. So we've got a sense of what's going on oh, that's not what I wanted to do. We've got a sense of what's going on initially. So now let's talk about before equivalence. What do you notice? Yeah, approximately the same slope, right? Minus that horrible blue line. I don't know if I can get rid of it. I guess I can't. I can erase it. So this was Caleb's hypothetical question. So guys, it's approximately the same slope, right? And what do you notice about the pH of the weak acid? It's understandably higher because it's weaker, less acidic. But now what we see is this idea that adding a strong base to an acid, whether it be weak or strong, basically does the same thing. It's consuming acid and the pH is rising. And then it gets to equivalence. And what do you notice about equivalence? Well, guys, first of all, let me add this spot. That is pH 7. What is the equivalence point? Not point, well, it is point, but what is the equivalence pH for the weak acid titration? It's above pH 7. Guys, why would that be the case? Go ahead. Do you see it, guys? In our strong titration, the salt that is formed is a worthless acid or base. It's the child of a strong acid and base and therefore worthless. But guys, in this titration, we are converting acetic acid into acetate ion. Acetate ion is not a worthless base. It actually reacts with the water. So the chemistry at equilibrium looks like this. I'll just rewrite it. So at equilibrium, the acetate actually attacks the water, and this is equilibrium, but the acetate, stop wiggling. The acetate attacks the water, and it forms this. And guys, pretend I circled that. The formation of hydroxide ion that is the result of the salt attacking the water causes the pH to be above 7. So at equivalence, for weak titrations, the pH will not be 7 because one of the ions that's formed from the salt that's the product will then attack water and change the pH. So if we're titrating a weak acid, the equivalence pH will be above 7. If we're titrating a weak base, the equivalence pH would be below 7. Yeah. And so we're going to play with that. And guys, this is going to be probably the hardest math you'll do all year. And it's not hard. It's just another iRace box. But trying to get into it, actually it's not. It's an ice box. But getting into it gets a little frisky. And I'll show you how that works. But now, guys, look at after equivalence. What's going on after equivalence? It's exactly the same. But doesn't that make sense? Because, guys, look at what we're doing. We are dumping base into an acid. And every molecule of base that we add, a molecule of acid gets consumed. And eventually all the acid's been consumed by the base. And it doesn't matter if it's a strong acid or a weak acid, it's still been consumed by the strong base. And if you go past that point of equivalence, it doesn't matter whether it was a strong acid or a weak acid initially, it's all gone. And now you're just dumping base into a solution that's as if the acid was never there to begin with. Now, guys, as you think about that, some of you might be going, wait a minute, with the weak titration, isn't there still a little bit of an equilibrium process going on behind the scenes because of the acetate? And the answer is yes. This chemistry is still going on, but it is so overwhelmed by the addition of the strong base that it's as if it's not even there. So it really, if you were to even do this with your lab data from second period, you can superimpose them and you'll see that they really do line up. Yeah.
So you established that the okay, now I just understand the question I was trying to answer.
You okay? Okay, so guys, well, actually, I shouldn't have done that. So you okay on the concepts? Now let's do the math. So guys, I'm going to hopefully be able to clean this up. And now we're going to bring this into the picture. And now let's have this conversation mathematically. Grab the piece of paper that I gave you. So now we are ready to talk about initial, before equivalence, at equivalence, and after equivalence. And now, guys, we are talking about the weak titration, the green curve. You're now at the bottom of my table, right? So, guys, initially, what is the pH, and we'll say the acid because that pertains to this graph. What is the pH of the weak acid? Well, it's no longer just the negative log of the concentration. That works with strong acids because they completely dissociate. So how do we find the pH of the weak acid? It's an ice box. Does that make sense? That you've got, let's just talk about acetic acid. The acetic acid, you know its molarity, in this case 1 molar. You know the molarity of the acetic acid. You can ice box that, and you can figure out the concentration of hydrogen by putting it into a Ka expression. Take the negative log of that, and that gives you pH. Is that okay? Okay, so guys, notice how I described that. What I said is this is equal to the ion concentration of the original equilibrium solution. That's the weak acid in this case. It could also be a weak base. And we study those using ice boxes, right? You okay with that idea? Okay. Now, guys, what about before equivalence? And Gavin, this is where you, given the conversation we had before, track with this. So guys, what about before equivalence? Well, that's here. It still doesn't work. So guys, that would be this area right here. So what is it that is making this solution acidic? What's the acid in this solution before equivalence? How much of it is there? How do we figure out how much of it there is? Well, it's an ice box, but how does it work? Well, guys, it's still a subtraction. And the idea is this. We know how much acid we started with in numbers of molecules. This is in moles. This is quantitative. And every one of those molecules and then every molecule of base that we add destroys one of those molecules of acid. So what then determines the pH? The amount of acid that hasn't been consumed. But it's not quite that simple because this is now a weak acid, and that weak acid goes to equilibrium. So guys, watch my hands. The big picture is this. How much acid did we start with minus how much base did we add? That difference will give us the amount of weak acid that wasn't consumed, right? Then we icebox that to figure out the pH. But guys, these two thoughts, these subtractions, we can do that in an ice box. So the initial amount of acid, the amount that was reacted, the difference gives us the adjusted concentration, and then that we can go change in equilibrium. So this fits into an ice box. Is that okay? Okay. Now, guys, the tricky one. This. the pH at equivalent. Oh wait, you know what we should do though? Let's go back and talk about how I described before equivalence. So I said it's equal to the concentration of the unreacted particle after it is allowed to reach an adjusted equilibrium. So that's the I-race box, but when we're doing this I-race calculation, we've got to keep track of the total volume. Do you see how that connects? So now let's go to at equivalence. And guys, it's not a big old 7 anymore. Why is it not a big old 7? Because one of the ions in the product salt will attack water and change the pH. So now what we have to do is we have to do an ice box. But guys, this ice box will not be an ice box that represents the chemistry of the titration. This ice box will represent the product of the titration attacking water. And we'll show you an example of that in a minute, but this is how I said it. The pH at equivalence is not 7 due to the hydrolysis of water by the resulting salt ions. This can be calculated doing Ka or Kb calculations, but that will be done in an ice box. You may want to add that. That'll be done in an ice box. And then guys, after equivalence, notice what it says. It's the same as a strong titration. It's just a quantitative subtraction because that's, again, the process is the same. We just have unreacted titrant that's messing with the pH. Mm-hmm. We don't mess with it. It is so insignificant compared to our titrant that it just fades into the background. We don't worry about it. When it's what? Yeah, and so the idea, remember, the entire idea of insignificant is comparative. So at equivalence, it is significant because it's the only chemistry in town, right? Once we reach equivalence, the only chemistry that's going on, because by definition, we've added equal amounts of base to acid, we've neutralized the acid. So it's gone. The only thing we have left is salt and water. So the titration chemistry is done. The only chemistry that's going on is the salt, specifically one of the two ions from the salt, attacking water. And because there's nothing else going on, that chemistry then becomes significant. But then as we start adding additional base, we now have some new chemistry going on because now we've got a strong component, and that strong component makes any of this weak component chemistry fade into the background, and we just call it insignificant. If you could zoom into this with infinite resolution, you would find that these don't exactly track over each other because there is a little bit of additional hydroxide that's formed by the hydrolysis of water by the acetate ion, but to reasonable approximation, they're the same, so we don't worry about it. So, guys, let's do the chemistry. Let's do the math, and it looks like this. So, made that for you. Okay, so guys, this is what this looks like. We are going to solve 2. That's plenty. It says this. It says calculate the pH of the solution that is formed when 45 milliliters of 0.1 molar sodium hydroxide is added to 50 milliliters of 0.1 molar acetic acid. You okay? So, guys, without knowing it, Gavin asked, well, I think he knew it was an important question. I don't think he understood the scope of his question. So when we were doing homework, Gavin said, how do I know when I icebox? How do I know when I subtract? How do I know what I'm supposed to do? And guys, I would suggest that when you get into problems like this, that question becomes critical. The reason it becomes critical is because if you are before equivalence, the math looks like this. If you're at equivalence, the math looks like this. And if you're beyond equivalence, the math looks like this. This math is an iRace box, this math is an ice box, and this math is a subtraction. And the math is radically different depending on where you are. So I would suggest that the first thing that you've got to do when you see one of these problems is figure out where you are. Now here's the problem. Most of you already know where you are because you understand that these are equal molar solutions. You understand this is sodium hydroxide and acetic acid. Did you notice I wrote acetic acid a little bit differently, hoping it might trick you? But all right, it's not. So guys, this problem is, no, this is this, right? That's this. This is the graphical representation of what we're talking about. And without knowing it, probably a lot of you in your brain went, hey, I'm at 45 milliliters, which places me somewhere in here, which means I'm before equivalence. But guys, the problem is that many times, like in homework and the tests, you're going to run into these problems and you're not going to know which side of equivalence you're on. So that is the first challenge in solving these problems, is locating yourself. Am I before, at, or after equivalence? So guys, what do we need to know in order to figure that out? Exactly. We've got to know the number of moles. Now let's talk about it. Let's talk about scenarios. Guys, what are we titrating, the acid or the base? The acid, acetic acid. So acetic acid, think through this with me, gang. Acetic acid is the thing we're titrating. Sodium hydroxide is our titrant. So what if we have more acid than base? Where are we on the curve? Before equilibrium, before equivalence. What if they're equal? We're at equivalence. What if we have more base than acid? We're beyond equivalence, but as Caleb mentioned, guys, all of that is by moles. Why is it by moles? Because sodium hydroxide is a strong base. So let's figure out moles. And guys, the math looks like this. We go 45. Oh gosh, 0.045? 2? Okay, so 0.0045 moles, and that's NaOH. And then we're 50. Is it? No, it's acetic acid. So HAC, so 0.0050 moles. So guys, again, I know we already know, but let's pretend like we don't. So where are we on the curve? Well, this is the thing that we're titrating. We understand this isn't always the acid. It feels that way, but you'll see in homework, we'll flip the tables. But guys, this is the thing that we're titrating. And you may find it helpful to do that, to physically circle the thing that you're titrating. So we are dumping sodium hydroxide titrant into acetic acid, which is the thing we're titrating. So which do we have more of? Well, we have more acid, more thing we're titrating. So what that means is we are before equivalence. Are you okay with that idea? So now that you've identified where you are, it's now time to go, okay, I understand where I am. How do I handle this? And if we're before equivalence, the answer is an erase box. So guys, what we're going to do is we are going to erase this. That's not what I wanted. So in order to erase this, we need a balanced equation, and that would be the dissociation of the acetic acid. So I'm going to go HAC, which I hope you're comfortable with, and then AC minus and H plus. So guys, that is the equilibrium that we are disrupting by titrating this thing. And then we go I, R, skip a space, C, E. And now we can start filling this in. So guys, it goes like this. And maybe we should remind ourselves, what does the I and the R represent? Well, yes, but what chemistry does it represent? The quantitative consumption of the acid. Then this represents the equilibrium being reestablished. So as you mentioned, these need to be in moles. So initially, how much acetic acid did we have? We just did it, right? It's this number. It's the 0.0050 moles. So we have 0.0050 moles. This is none, and this is none. Now, how much of that acid is being reacted, is being consumed? The answer, how much base did we add? 0.0045 moles. So we added 0.0045 moles. Now guys, let's talk really quickly. Can we do this? So check this out. What are we going to do with this mathematically? We're going to subtract it, right? This is how much of this we started with. This is how much of this went away, because that's how much base we added. So guys, I know you want to poke your calculators, but watch. Do you see the connection between this and this? Some people teach this by simply saying, do the subtraction right there. As we did when we dealt with strong titrations. Same idea, right? How much base or how much acid did we start with? How much base did we add? Subtract the two, realizing that we wrote them in the wrong order, and it should always be positive because you can't have negative amounts. We talked about that. And then the question, you could just do the subtraction right here. And you could, but here's the problem. This is why I don't teach it that way. Because if you do the subtraction right here, many times you forget to talk about what it does to acetate. So that's why I don't teach it that way. And typically at this point, somebody out there will raise their hand and go, wait a second, why can't we just do the subtraction back here just like we did with strong titrations? And my answer is, because if you do that, all that does is tells you about this change, and it neglects the change to acetate. And so I find it valuable to do this in an erase box. So this then will go up by 0.0045, and this is unchanged. Do we need to talk about why it's unchanged? Guys, what's the chemistry that's going on? Remember, we are adding hydroxide. Make sure you're clear on this. We are adding hydroxide. So the hydroxide is stripping a hydrogen off of AC, right? Where does that hydrogen go if it doesn't go here? It makes water. So the hydrogen concentration at this point is not changing. So when we bring these down, then we've got, you guys know how I struggle with this, 0.0005.
Yes.
Oh, look at me. And then 0.0045, and then 0. And then 0. Yeah. I'm sorry? Yeah, so technically these are tied up in hydronium. Yeah. So now, guys, what do we need to do? We're not ready to icebox yet, because what do we need for our icebox? Molarities. So you'll notice I wrote these a little skewed to the left, because what we've got to do now is divide by the volume to get our molarities, right? So 95 milliliters. Okay, so is that 0.09? Yeah. So divide that by 0.095 and 0.095. So 0.0005 divided by 0.095, and I get 0.00, I'm just going to put 53, and then 0.0045 divided by 0.095 is 0.047, and then this is still 0. Now we're ready to icebox. So now we go minus x, plus x, and plus x. So this would be 0.0053 minus x, 0.047 plus x, and x. Now, guys, for time and space sake, I'm going to take some liberties with solving it from here. We would go Ka is equal to the concentration of acetate ion times the concentration of hydrogen divided by HAC. We'd go from there. But I'm just going to go 1.8 times 10 to the negative fifth is equal to 0.047 plus x times x divided by 0.0053 minus x. And then, guys, at this point we would do the approximately equal to, right? And we would get rid of these x's. And then solving this, we'd have 1.8 times 10 to the negative, 1.8 times 10 to the negative fifth. And we will divide that by 0.047, multiply that by 0.0053. And now I have my value for x, and then we would take the negative log of that. And were you okay with everything I did but didn't represent? Is that okay? So, guys, I get a pH of 5.69. Can you confirm that? Is that right? Okay. So, and guys, I'm sorry if do you want to talk about the math at all? I know I was babbling and poking my calculator. Yeah. Yeah. No, but you do need to show this would not be okay. you would have to do approximately equal to and then 0.047x divided by 0.0053. It used to be that you did. You had to write a little sentence that said, I am disregarding the x's because they're insignificant compared to the initial concentration. Now they just let you do the approximately equal to. So what do you think about the concepts, the locating yourself, the math, the subtractions, the I-race? You guys okay? Okay. Guys, this is about to get a little nutty. Can I get rid of this? Okay. So take a look at this. Calculate the pH at equivalence. So guys, and I'll let you write it down. But the first thing that we need to do once you've got it written down is we need to have that conversation again about locating yourself. What do you know? Can we try locating yourself? So, guys, let's stand back from this a little bit mentally and let's read it. So it tells you you're at equivalence, right? It just lays that out for you. You're at equivalence. And so we notice that the molarities are equal. So we know we've got equal molarities. So if the molarities are equal, and it tells us we've got 50 milliliters of acid, how much base do we have to have? Also 50 milliliters. Now guys, all sorts of things they'll throw at you. Now what if they told you you were at equivalence, but the concentrations were different? What would that then tell you about the volumes at equivalence? They will also be different, but here's the problem. You need both of those volumes because eventually you're going to use them to calculate a new molarity. It's kind of an evil trick. But if they give you different molarities, you would then have to do a little backwards dimensional analysis to figure out the other volume. Now guys, what if they did this? What if they didn't tell you you were at equivalence and they just said well, let's say it. What if they said 50 milliliters of 1 molar acid, or 0.1, 50 milliliters of 0.1 molar acid, 50 milliliters of 0.1 molar base? If they told you that, what would you know? We're at equivalence because it's same volume, same molarity. But what if they told you volume of one and volume of the other, but they had different molarities? Then you've got to calculate moles. Does that make sense? That's that whole idea of locating yourself. That's this entire conversation. You've got to calculate moles. Now guys, what if you do the moles calculations and the moles are equal? Then you're at equivalence. Do you see where that's headed? So there's lots of different ways that they can get you into these equivalence calculations. They can tell you that you're equivalence, or they can give you the volumes and the molarities that lead you to equivalence, because when you figure out moles, they're the same. Regardless of how you get there, what does the chemistry look like? And guys, this is where this gets interesting, because at equivalence, the chemistry has nothing to do with this and this. That is not the chemistry of equivalence. So what is the chemistry of equivalence? Well, guys, do this with me. You're all okay with the idea that we're at equivalence, though, right? So once you establish that you're at equivalence, you've got to figure out what is the chemistry that I'm actually studying. So guys, this is the first step. So you do the moles calculations. Oh my gosh, the moles are the same. I got to figure out the pH at equivalence. The first thing you got to figure out is what chemistry am I actually studying? And the answer is this. This is the chemistry of the titration. But this is not the chemistry of equivalence. Why not? Well, guys, at equivalence, how much of this is there? None. That's the idea behind equivalence. You have added an equal equivalence. You've added an equal amount of this as you have this. This is all gone. This is all gone. This is what is sitting in the beaker at equivalence. There's no reactant left. It's quantitative. It's all gone. That's gone. So if this is what's left, what do we know about sodium? Child of a strong base, making this what? So guys, this then is the chemistry of equivalence. It's acetate attacking water. And that is what you're going to icebox. So in order to figure out what's going on at equivalence, that is the chemistry that we have to icebox. So let's get ready to icebox. And let's just do this, because we don't need to worry about that. So guys, where on earth are we going to start this icebox? What do we need to know? The molarity of the acetate ion. But where are we going to get that? Because it's not 0.1 molar. Guys, this is what the calculation looks like. Please don't write this down. But you've got to understand the logic behind it. Guys, where did the acetate ion come from? So guys, the acetate ion came from acetic acid. So the idea is this. We, in the titration, took HAC, and by adding OH to this, we created acetic or acetate ion. Does that make sense? So how much acetate ion do we have? How much acetic acid did we start with? That's the answer to the question. So guys, in order to figure out how much acetate ion you've got to figure out how much acetic acid you started with. So how do we figure out how much acetic acid we started with? Dimensional analysis. So it goes like this. We've got 50 milliliters. So we go 50 milliliters of HAC, AC, and we go 1,000 milliliters. And guys, if my pen drags, I'm not going to try to fix it. And this is, sorry, I got to do this. 1 liter is 0.00 moles, and this is 0.00550 moles of HAC. So that is how much acetic acid we started with. Is that okay? So how much acetate ion do we have right here? The same amount, 0.005 moles, right? But don't write it down, because that doesn't fit in an icebox. We need a molarity. We now know that we've got 0.005 moles of AC, but how much water is that dissolved in? 100 milliliters. So over here on a side calculation, we can go molarity is moles divided by liters is 0.0050 divided by 0.1 liters. So is that, no, yes. So is that 0.05? Okay, so we've got we've got 0.05 molar and 0 and 0. Now we can icebox this. This goes down by x, this goes up by x, this goes up by x. So this is 0.05 minus x and x and x. So now, guys, this is where this gets really exciting. What are we going to do now? Not Ka. This is Kb. So Kb is equal to concentration of HAC divided by the concentration of OH, all that divided by the concentration of our base, AC minus. Now, guys, you ready for this? Where do we get the Kb for acetate ion? Guys, the relationship is this. Kw is equal to Ka times Kb. So 1 times 10 to the negative 14th is equal to x, no, is equal to 1.8 times 10 to the negative 5th, which is the Ka of acetic acid, and that then allows us to solve for the Kb of acetate ion. So we've got 1 times 10 to the negative 14th divided by 1.8 times 10 to the negative 5th, and we get 5.6 times 10 to the negative 10th. That then goes in here, and we go 5.6 times 10 to the negative 10th is equal to x squared all over 0.05 minus x. And again, guys, we do our approximately equal to that I don't have space for. And we get 5.6 10 to the negative 10 times 0.05. And then take the square root of that. And I get 5.3 times 10. Please just write. Times 10 to the negative 6. Did you get that as well? Okay, so now what does that tell us? What is that value? Concentration of OH. So if we go 5.3, and again, guys, you should write this out, but if we take that number and take the inverse log, we then get a POH of 5.28. Subtracting that from 14, we get a pH of 8.72. And again, you would show that work, but we're running short on time. Did you guys get 8.72? So now let's contextualize this. If the stars lined up which we hope they did, we would then see that that pH is at about 8.72, which is where we would expect it to be. The graph isn't perfect, but that's actually the value is 8.72. Are you good? I will in a second. So guys, here's then an interesting question that I'd like to address before I bring the math back up. What about this? What would the math look like if we were beyond equivalence? So what would we do? Well, guys, we would start with this, right? We would identify our number of moles. We would start here. And what would it look like if we were beyond equivalence? Well, we would have more moles of strong titrant than weak thing being titrated. So you would then know you're beyond equivalence. So what do you immediately do? Subtract them. And that will give you the amount of additional base that's present. Once you've done that subtraction, you'll convert that to a molarity by dividing by the adjusted volume, and then take the negative log, and that gives you pOH, and you go from there. So again, guys, this entire process hinges on this first calculation that allows you to identify where you are. In summary, if you're before equivalence, you I-race box it. If you're at equivalence, you ice box it, but the chemistry that you ice box is the chemistry of the conjugate. And then if you're beyond equivalence, you just subtract, convert it to a new molarity, and go from there. You get the idea? Okay. So, guys, here is your homework. And here, Spencer, is that math. And with all that said, sorry, this is going to screw things up.